So, what is the definition of free fall? What does it mean? When we talk about free fall, what is that? Falling what? Other influences. So what's the only thing that is influencing the object? Gravity. Just gravity. Okay? So when an object is in free fall, that is your definition. So you got to remember that. You might want to jot that down. Means that the object is free from other influences and then gravity. So gravity is the only thing that is causing that object to go down, to go to the ground, and that is the force of gravity. So it does not depend on the object's mass. It does not depend on what the object is. It does not depend on anything other than gravity. Okay? So that is important to remember because it's not always what we see. So if you look there, free-falling objects are always accelerating, so you need to know that. Free-falling objects are always accelerating. For an object tossed in the air, the acceleration is the same on the way up and on the way down, regardless of whether it's thrown upward, downward, or just dropped. Okay, so if I take this ball and I throw it up, okay, the acceleration going up is the same as the acceleration coming down. Okay, whether I do this, and drop it, or whether I just drop it, or whether I throw it up in the air, it's the same. Okay, the acceleration going up is the same as that going down.
Wait, what?
So
what if I chunk the ball up?
You chunk it up?
Yeah, as hard as I can.
Okay.
Wouldn't the acceleration?
Acceleration. We'll probably get to that one. But we talk about if you chunk it, is it necessarily in free fall? When is it in free fall? So when we're talking about free fall, we're talking about the only influences on it being gravity. Okay? So keep those things in mind. Then we'll start doing some problems and looking at different aspects of it. Oops. So acceleration is produced by gravity at the Earth's surface, and it's denoted with a G. Okay, so before, all of our acceleration equations have had an A in it, right? A for acceleration. Well, when this particular chapter, or this particular part of this chapter, our acceleration, if an object is in free fall, is represented with a G. Okay, G for gravity. And it is a constant number. As I said, it's the same whether we throw it up, whether it's coming down. Acceleration due to gravity is the same number. Memorize that number. I will not give you that number. In a problem, all they'll say is the object is in free fall. You are expected to know that that means acceleration due to gravity is 9.8 meters per second squared.
Wait, so I gotta remember every single one of them?
There's only one.
Changed in Hong Kong.
Not enough for us to worry about. Right? Because if you look at the table, it is 9.79 as opposed to 9.8. That's not enough for us to worry about. Okay? That's just showing you that it is due to gravity. And the force of gravity is not the same everywhere in the universe. If we go to the top of Mount Everest, the force of gravity is a lot less than it is at sea level than it is on literally at sea level. If you went to New Orleans, which is actually below sea level, and you compare the gravity there to the gravity on the top of Mount Everest, it's going to be different. Now, the difference is going to be small, as you see, teeny tiny, but it's still different. If you went to the moon, of course, it would be dramatically different than here on Earth. Okay? So that's just showing you it is due solely to gravity, and gravity does change slightly depending on where you are. Yes.
So, what planet is has like a super high gravity? Jupiter.
I think it is Jupiter.
So if we
Maybe Saturn. Is Saturn more than Jupiter?
I would assume Jupiter.
I think Jupiter's the most.
So if
Yeah, because it depends on the object's mass. So Jupiter, if Jupiter's one of the bigger planets mass-wise, then it's going to have a stronger force of gravity.
So if we lived there, would we have like tree trunk legs?
Yes, and you would probably be very, very short and very stocky, you know, as opposed to somewhere else where you might not need as much muscle or whatever, if you could do that. Okay, so the 5 constant acceleration equations of motion can be used to determine the position and velocity of a free-falling object by substituting g for a. So all of those equations that you learned at the beginning of chapter 3, they're the same equation, but instead of a, we put g. So instead of telling you what the acceleration is in the problem, they're going to let you have to remember and assume, oh, it's always 9.8, okay? So in your problems, they won't tell you acceleration is whatever. They will say the object is in free fall, or they will tell you the situation and you're going to have to discern that the object is in free fall, and so the acceleration you're going to use is 9.8. What about the sign? Got to remember that sign. What does the sign of acceleration indicate? The direction you're going in. Whether you're going with gravity or going against gravity. Okay? So in this particular case, if you're going with gravity, that would be positive. If you're going against gravity, that would be negative. Okay? All right. The velocity of an object in free fall increases linearly with time. Okay, so, and that should make sense. It's just a fancy way of saying, if I drop this ball, every second that it's in the air, it's going 9.8 meters per second faster, which means right before it hits the ground, it's going to be going its fastest speed.
Wait, I thought we just said it was always accelerating. Doesn't mean acceleration is changing. Just kidding.
Right, exactly. Good. Don't second guess yourself. You were right. Okay. The distance increases with time squared. Okay. So if you're talking about how far is it going to wind up falling, that's going to be it increases with time squared. So you're going to use that formula. Like I said, all those formulas that you learned at the beginning that are on page 80. What is that? 88. Yeah. All of those formulas are going to be exactly the same, but wherever there's an A, there's a G. So the final position is equal to your initial position plus your initial velocity plus 1/2 times squared, AT squared. So if we didn't chunk it, just say we dropped it, what's our initial velocity? 0, right? If I just drop this, it doesn't have an initial velocity because I dropped it. I didn't push it, okay? So its initial velocity is equal to 0, which means, let's write that formula up here. XF, XI, VIT plus 1/2 gt squared. G just means a, acceleration. So that's going to fall out to 0. Its initial position, of course, is going to be 0. So its final position is just dependent on gravity, how long it stays in the air. Okay. So same equation. You don't have to memorize anything new. Same equation. It's just we're replacing A with G. And then, of course, if we're dropping it from a building, those other variables are going to fall out to 0. And so your equation is going to kind of collapse down. And it's just dependent on the gravity and how long it stays in the air. Yes?
So why is your T 0? Because the start is.
Because 0 times anything is 0, right?
Yes, ma'am. I'm so sorry.
No, you're fine. That's exactly right. That's what you need to be.
That's very good.
That's what you need to be recognizing and answering. So that's fine. All right. Okay, so here is a graph of an object in free fall. Okay, it is not a straight line, obviously, and it is an upside down parabola. So let's look at what is happening at each stage of the object in free fall. Let's see if this is anywhere in your book. Yes, this is on page 101. So position and velocity change differently in free fall. So look at page 101, or you can jot this down. I would jot this down in my notes. The position time graph of free fall motion reveals some symmetry. It's a parabola. So that means it's going up to a peak, and then it's coming down the same exact way on the other side. So here's our initial velocity. So if it has an initial velocity of 29.4 meters per second, what does that mean that we did with this ball, Cappy? Well, this ball has an initial velocity of 29.4 meters per second. What does that mean? What did I do? I threw it up, okay? Threw it up in the air. It rose to a certain point, and while it's going up in the air, it is accelerating 9.8 meters per second squared. Okay, so at 1 second, it is going, now notice, what's it doing? What's happening to the velocity as we go up? It's slowing down. Why is it slowing down? Oh, it's going against gravity. Exactly. The velocity is going in one direction. Acceleration due to gravity is going in the other. So that's slowing it down. Okay? Eventually, it's going to keep slowing down, so eventually it has no velocity at the top of its peak.
But it still has acceleration.
What is happening to, when it reaches that 0 velocity, what's going to happen to it eventually? What happens to all things eventually? They come back down, correct? Why is it coming back down? Gravity is pulling it back down. Okay? So now it's coming down. So its acceleration is 9.8 meters per second down, but its velocity is slowing down. So look at the velocity. It's the same magnitude, but look at that sign. Negative. Why is it negative? Not that it's traveling backwards or anything. What's it doing? It's going in the opposite direction from where it started. So went up, goes up, okay, then comes back down. Right? So it's the same velocity on both ends, because the only thing that it's due to is acceleration due to gravity. So that negative sign just means the direction in which it's traveling. Okay? So that's why you'll notice that on the other side it's negative 19.6 meters per second. And it hits the ground, or right the split second before it hits the ground, its velocity is negative 29.4 meters per second. That means it's going to end up with the same magnitude of velocity that it started with, but its direction is different. Instead of going up, it's coming down, and it's right about to hit the ground. Okay?
How does it have the same, oh, wait, okay. I'm trying to connect velocity and acceleration. Never mind.
Okay. All right, think about it. Yeah, try and process it, think about it, and then come back to it in a minute. Because I believe, yeah. So we got all the time in the world to sit here and process that because that's the end of my slide presentation. The only other thing we're going to do now is we're going to work